Okay, it's all good. Okay, so this is at the moment just the variance of everything which I've just done there. Okay? So now let's think about what we can do here. Would you be happy that I can split that up into the variance of x1 over 5, plus x2 over 5, plus x3 over 5, plus x4 over 5, plus x5 over 5? Okay? So in general, it's going to be each individual random variable divided by each one of those n's. Yeah, I'm literally just splitting that up into x1 over 5, x2 over 5, x3 over 5, etc., etc. Okay? So, would you be happy that that is true, what I put on the screen there?
Yes.
Why has it got to be true? Well, have a think, because it's not always going to be true, is it?
Because it's independent.
They're independent. If it's not independent, then you just take away the covariance. Okay?
Yes.
But we're assuming all of these suites are independent of each other. Okay? Which is a pretty big assumption, but I think we can make it here. Okay? Because they're all independent. So in other words, what we've got is the variance of, in this case, the variance of x1 over 5 plus the variance of x2 over 5 plus the variance of x3 over 5, etc., etc., etc. I've run out of space. But it's going to go all the way through until we've got xn over 5, or xn over n. So in that case, x5 over 5. Does that make sense? Okay, now just have a think about your variance algebra. Okay, so I put it on the screen, but just remind myself, okay, if I have the variance of a times some random variable, what is that equal to?
A squared variance.
Perfect, got it. Times the variance of y. So in this case, if I want to pull out that 1/5 from each of those variables, I need to pull it out at the start. So it's going to be pulled out as 1 over 5 squared. Yeah? So it's going to be 1/5 squared times by the variance of x1 plus 1/5 squared times by the variance of x2, etc., etc., etc. Does that make sense? Okay? Now how many times am I going to have that being added to itself? N times, right? Because I'll have 5 of them in total. So in other words, what I will have in total, I think we can squeeze it in. In this case, I'm going to have 5 of them. So it's going to be 5 lots of 1/5 squared of the variance of x, whatever it is. Okay? Because in this case, the variance is always going to be the same. Okay? Can do a bit of cancellation. 5 times 1/5 squared is just going to be 1 over 5. Okay? So actually in this case, this is going to be equal to, in fact I think we can write it out underneath here. It's going to be a bit messy, but it doesn't matter. It's going to be the variance of x, so the variance of each of these individual suites, divided by the number of suites which I've got. So bring that over here, okay? Would you be happy that this thing that goes here is going to be the variance of the original distribution, which is 3 squared, divided by 5. Absolutely. So this here is how you combine together each of these individual random variables. So if you go out and you collect a sample of, in this case, we've got 5 suites, okay, which are all distributed using this distribution, the mean of those samples should now be distributed using the same mean, but the variance has changed by a factor of n. Okay, it's been reduced by a factor of n. So in general, if you have a random variable which is going to be normally distributed with some mean and some variance, okay, if you take the sample of n of those individual random variables, they are going to be normally distributed with the same mean. That makes sense. However, the variance will change by a factor of n. So it's going to be divided by n. That makes sense?
Yeah.
And this makes sense with what we were doing up here. Because have a look, as n approaches infinity, we said that the sample mean should approach what's happening at the population level. In other words, that shouldn't really change that much. It shouldn't change at all. But the standard deviation will decrease. And in fact, the way that it decreases by a factor of n for every n that you increase. Yeah?
Yes.
You happy with that? Okay, good. So, if we come back to the question then, we now have this going on. So as n equals 5, we now need to find this. The way in which we answer the question is exactly the same as we answer the question with n equals 1, with 1 chocolate bar. Okay? We just simply do the same standardization, however, we use now this distribution here. Okay? So in other words, when we do our standardization, so we want the probability that x bar is less than 48. When we do our standardization, we take our 48, same as before, we take away our mean, which is 50, and we divide by our standard deviation. So what's the standard deviation of 3 squared over 5 going to be? That's the variance.
1.6.
Well, yeah, so it's going to be 3 divided by the square root of 5. Have a thing, because the formula for z is x minus mu divided by the standard deviation. So if that is my standard deviation squared, that's my variance, so that's equal to 3 squared over 5. What is my sigma going to be? What's my standard deviation going to be? The square root of that. So if I square root this, square root of 3 squared is just 3, square root of 5, I'm just going to write as 5. Is that okay with everyone? So the method which you answer these questions is no more difficult. People look at people look at the central limit theorem and they get really, really worried. They think this is really hard. It's not. All you understand is that instead of just taking one random variable, you're now taking a selection of random variables. And you understand the core idea, just 2 things you need to understand. The mean stays the same and the variance decreases by a factor of n. Literally this idea over here. This is all the central limit theorem tells you. So if in the exam I say, right, go out and select a sample of 5 chocolate bars, now find me the probability that the mean of those chocolate bars is less than 48, you answer in exactly the same way, it's just you use a new distribution. And the new distribution, the only thing that changes is that, the variance. Is that okay with everyone?